All right, let's talk about double displacement reactions. So the first step with any problem like this is figuring out what sort of reaction you are dealing with. So how can we tell if this reaction is a double displacement or not? And the way that we tell is double displacement reactions will all have two aqueous ionic compounds as our reactants. So what does that mean? Ionic compounds are almost always compounds that have a metal and a nonmetal. Sometimes you'll have polyatomic ions in place of either of those. For example, in here we have sulfate and phosphate as our nonmetal. These metals could be replaced with stuff like ammonium or other positively charged polyatomic ions. But in this case, we have metals and nonmetals. Aqueous is displayed right here with the AQ. And what that means is that these compounds are disassociated in water. So we have two beakers, each with water. And by themselves, these compounds are bonded by their opposite charges. But when you put them in water, they disassociate into their individual ions. So in this beaker, we have a bunch of free-floating coppers and a bunch of free-floating SO4s. And then over here, we got a bunch of free-floating sodiums and some free-floating BO4s, phosphates. This is because water is polar, I think. I'm not sure, but they're dissolved. And when we combine these together, our ions are going to get displaced. They're going to switch places with each other, and we will end up with two new compounds on the other side of our equation. Before we do that, though, it's important to start balancing our equation, and the way we do that is by checking out the charges. So, excuse me. Let's start with sodium phosphate. We can take a look at our periodic table, and sodium is in our +1 column. So let's go ahead and use this blue dice to denote +1, and we have 3 of those. So we're going to put 3 +1s, right? Therefore, we know that our phosphate must have a charge of -3 to counteract with that. So there's our first compound. It's got a +3 and a -3 in there. Nice and bonded. On this other side, we have copper, which is a transition metal. So we don't know what charge that is. So we can take a look at our list of polyatomic ions, and we can find sulfate all the way down at the bottom with a charge of -2. And that lets us know that the copper that we are dealing with must be copper 2 with a +2 charge, and sulfate has a -2. There we go. However, these are not balanced, because if these were to switch places, we'd have a +2 and a 3 and a -3. And those don't equal each other. So let's make them equal each other. And how do you make a 2 and a 3 equal each other? Well, by multiplying them by each other. Just like that, over here we have a total of 6 sodiums and 2 phosphates, which gives us a -6. Over here we have 3 copper 2s for a +6 and 3 sulfates for a -6. And then they're balanced. Now we can go ahead and start writing the other side of our equation. So first let's switch our copper with our sodium and write our copper phosphate. It's important to keep in mind how many of each you have. So we have 3 coppers and 2 phosphates. That doesn't simplify any further, so we're just going to write it as is. 3 coppers and 2 phosphates. Let's not write our aqueous yet, because we do not know if it is soluble. And then our other new compound is sodium sulfate. And we have 6 sodiums and 3 sulfates. This does simplify. That means we have 2 sodiums for every 1 sulfate. However, we don't just have 2 sodiums, right? We have 6 sodiums, and we don't just have 1 sulfate, we have 3 sulfates. So what does our coefficient need to be? It needs to be 3. That way we have 3 sulfates and 6 sodiums. There we have it. There's our balanced equation. Now we just have to figure out if these are aqueous or solid. And to do that, you take a look at your solubility chart. Let's start with copper phosphate. And you can see phosphate is right here in our insoluble compounds, with the exceptions of alkali metal ions and the ammonium ion. Copper is neither of those things, which means that copper phosphate is insoluble. That means it stays as a solid. It does not dissolve. Our sodium sulfate, on the other hand, you can see sulfate is right at the bottom of our soluble chart. With a whole bunch of exceptions, sodium is not one of them. So this does dissolve, and it is aqueous. There we go. AQ. Now we can go ahead and write our complete ionic and our net ionic charges or equations. First, with our complete ionic, we're just going to split up all of our aqueous solutions into their individual ions and write their charges. So one at a time, we have 3 coppers, all with a +2 charge, and they are aqueous. Plus we have 3 sulfates, all with a -2 charge, aqueous. Plus we have 6 total sodiums, all with a +1 charge, aqueous. And we have 2 phosphates, aqueous, with a -3. There we go. Now on the other side, when something is solid, we're not going to split that up because it's not dissociated into its individual ions. Instead, it's just itself. So let's write that as is. Copper, phosphate, and solid. No need for charges. And then once again, we have 6 subscript 2 times the coefficient 3 sodiums and 3 sulfates. -2. There we have it. There is our complete ionic equation. Last but not least, we need to do our net ionic equation, which is where you just write down the only things that changed throughout our equation. Anything that stayed the same, we can get rid of. So let's look for things that changed. This copper does change. Over here, it's aqueous, and over here, it's part of a solid compound. So that is going to be included in our net ionic. Our sulfate, 3 sulfate aqueous, stays the exact same, so we do not need to include that. Same with our sodium, stays the same, and our phosphate does change. So these are the 3 terms that we need for our net ionic equation. Aqueous plus 2 phosphate goes to copper phosphate. Once again, no need to write the charge because it's solid. And there we go. We can double check our work by making sure all of our numbers of our elements are the same. So on this side, we have 3 copper, 3 copper, 3 sulfate, 3 sulfate, 6 sodium, 6 sodium, 2 phosphate, and 2 phosphate. Same thing over here. Copper, copper, sulfate, sulfate, sodium, sodium, phosphate, phosphate, and here as well. And there we have it. That was a double displacement reaction, how to identify one and how to balance their equations and how to figure out what precipitates at the end.